Good morning, everybody. As Jim mentioned, I'm Nishan Pethiyagoda. I'm a lead field engineer with Hilti Incorporated. And my presentation today is going to be on anchor principles and design. Basically, after we finish this presentation, what you should be able to take away from it is understanding how the different failure modes and working principles of post-installed and cast-in-place anchors work under various loading conditions. You should be able to evaluate the various factors that affect the performance of different anchor systems. Hopefully, at the end of this, you would have gained confidence in being able to understand the building codes and also the ICC evaluation services reports. And you should be able to utilize the different resources that are available to you to help you select and design with adhesive and mechanical anchor systems. So, the agenda for today, what we're going to talk about. We'll talk about building code requirements and acceptance criteria. We'll talk about different anchor types and the classification of those anchor systems. We'll go through the fundamental principles of anchor theory, and I'm going to focus on a little bit on strength design. I promise I won't get too technical on this stuff, but I wanted to touch on strength design for anchors. We'll talk about anchor design influence factors, how you would go about selecting the right anchor for your particular application, some of the design resources that are available to you, and then we'll open it up for questions at the end. So, anchoring applications. Some of the very common applications for anchoring include attaching steel base plates to concrete, so for columns or steel beams to concrete. So things like scaffolding tiebacks could be anchored down, and safety-related anchoring, so anchoring fall restraint systems, common application. Anchors are also used for rebar doweling applications when you want to do things like extend floor slabs or concrete elements. And anchors can be used to attach to both masonry and concrete. And with masonry, I'm talking about both solid masonry and hollow masonry. So grout fill block, hollow block, clay tile, brick, all are suitable for anchoring applications. Now, a critical anchor connection is one where failure might result in loss of life, a lot of structural damage, or significant loss of property, right? I remember about 15 years ago receiving a frantic call at about 7 a.m. in the morning from this contractor saying, hey, can you get out to this job site in Portland, Oregon? We've got this 15-story building going up, and the scaffolding is separating from the building. It had been anchored into the concrete floor slabs, and it was starting to pull away. Okay? Got out to the job site, found out that there were actually people working on that scaffolding when it started to separate, when it started to pull away. That is a critical connection. Okay? So, it is important to understand the fundamental principles of anchor theory in order to be able to properly select an anchor system and to design with it. And what we're going to do is talk a little bit more about the fundamental principles of anchor theory. Before I do that, the code criteria, the code landscape right now, particularly in the United States, there's one basic model code that actually encompasses the majority of the design methodologies for anchor systems. And that's ACI 318, currently in the 2014 edition. Anchor design is found in Chapter 17 of that code. Both the International Building Codes and the AASHTO codes reference this particular design methodology, or the ACI 318 design code. And basically what the ACI 318 design code offers is it has certain sections, ACI 355.2 and 355.4, which are anchor test standards, which enable manufacturers to actually get their anchors tested to show compliance to building codes. So there's an organization, ICC, the International Code Council, which has developed their acceptance criteria harmonized with ACI 355.2 and ACI 355.4. And what ICC does is it takes manufacturer data or products, has an independent test agency evaluate those anchor systems, and then publishes reports offering those anchors recognition to building codes. Similarly, the AASHTO Bridge Design Building Code also references the ACI 318 manual. So if you're working on AASHTO projects, that's available. What ICC offers? One is you're assured that the product that you might be utilizing actually does meet industry standards and has been qualified if it has an ICC approval. So if you look for that logo, the ICC Evaluation Services logo, you know that that product has been qualified. And as I mentioned, this is a nonprofit organization that actually tests building products and offers them compliance to building codes, or recognition for building codes. ICC reports, if you haven't used them in the past, they're laid out in a very standardized format. These reports are available free of charge to everybody. You can go on the ICC website and download them. Most manufacturers have ICC reports on their websites as well for their particular products too. But the ICC reports are laid out in a very standardized format that enables you to do a quick check and do your full design actually utilizing the ICC reports. So in the standardized format, like for example, Section 1 has evaluation scope, Section 2 has uses. One that I particularly like is Section 5, conditions of use, which in bullet point tells you all the limitations of these anchors as well. So if you have a condition where you're comparing two anchors to figure out which one is the right one for your particular application, that's kind of the first place that I look at. All right, are these two comparable? Are we comparing apples to apples when we look at anchors? The ICC reports also include things like the design tables. So as an engineer, what you need to go in there and do your designs. It includes examples so that you can actually do your hand calcs, follow along to figure out exactly how the design is done. And something that's pretty important too is it includes the not design parameters, but installation parameters. So basically the installation instructions for particular products are also included in ICC reports. And I should stress, when it comes to anchor design and anchor installation, it is very, very critical that the installation instructions that the manufacturers publish be followed when the installation is being done. I've heard of situations where, somebody goes, all right, this anchor is supposed to be installed with a 5/8 inch diameter drill bit, but I don't have a 5/8, so I'm just going to use a 3/4 inch diameter drill bit. That does not work, okay? You could lose significant capacity of those anchor systems by going that route. But that's something else that these ICC reports offer. So design methodologies. There are two main design methodologies when it comes to anchor design that are utilized: allowable stress design and strength design. Allowable stress design is kind of the older method that's kind of being phased out. And basically, what allowable stress entails is in development of data, it was very simple for us as a manufacturer to do that. What we did was we had to test 5 anchors to failure, right? Take the average of that, apply a safety factor, and we could provide that information to whoever is utilizing the anchor system saying, this is the allowable load that you can use. So test 5 anchors, take the average, use the safety factor, and that's the loads that you would use, okay? The new methodology has shifted to actually testing various different possible failure modes. Things like steel failure, concrete breakout, pull-out, bond failure, and things are all tested in evaluating these anchor systems. Something else that has been incorporated into the strength design methodology is now there's a coefficient of variation assigned to your anchor system, to the test results. So if you get a large scatter with your test results, you get penalized for it. And I just want to kind of highlight why this is important. So take with the allowable stress design method, okay? I test 5 anchors. 2 of them resist 4,000 pounds. 1 of them gets up to 2,000 pounds. 2 of them get 0, all right? They just fail, they pull right out. With the allowable stress design method, now if I was going to be taking that data, that's 4,000, 4,000, 2,000, 10,000, I divided by the 5 samples that I had to get the average, apply a safety factor of 4, and I come up with 500 pounds. Would you feel comfortable utilizing an anchor and saying that it can hold 500 pounds if you knew that 2 of those anchors got 0 load, okay? So that's where the predictability of strength design comes into play, where it becomes a lot more, a better system to actually evaluate anchor design. So anchor types and classification. Before I start talking about that, I want to talk a little bit about anchor loading conditions. So basically, anchors are loaded in tension and shear. Those are the primary loading conditions, or a combination of the two as well. It could be combined loading that's acting on the anchor as well. And the anchors also, the loading can also be broken down into 2 other additional categories. That's static loading and dynamic loading. Static loading is when the load actually remains constant through the life of the anchor. So say, for example, the weight of scaffolding, the weight of the actual assembly might be considered as, the static load, the dead load. Dynamic loading varies in magnitude and frequency through the life of the anchor system. So examples of dynamic loading, wind load, the people working on the scaffolds, moving around, carrying equipment and all that, that would be considered more the live loads, the dynamic loads that would be acting on these anchor systems. Anchor types. Basically, anchors can be broken down into two main categories. You've got the cast-in-place anchors and the post-installed anchors. The cast-in-place anchors are actually placed before the concrete is poured. The post-installed anchors are installed after the concrete has cured. The post-installed anchors can further be broken down into two categories. You've got the adhesive systems and mechanical anchor systems. The adhesive anchor systems, they offer different advantages. The adhesive anchor systems, you have to wait until the adhesive has cured up before you can load up the anchor systems. The mechanical anchors can be loaded immediately. However, on the other side, adhesive anchors give you a little bit more flexibility in embedment depths and things like that that you can utilize. So which one you use depends on the preference of the designer and also the contractors. Anchor load transfer mechanisms. This slide illustrates the basic tension load transfer mechanisms for the majority of the anchor systems. And I say tension load transfer mechanisms because shear is almost always transferred by a bearing on the concrete surface. And if you look at the majority of the mechanical anchors, the way they transfer their tension loads is via friction. So if you take, for example, a wedge type anchor, all right, that's what's shown over here. You get the wedges over here, the anchor is installed, there's an expansion cone. When that anchor is torqued down, what happens is the wedges ride over that expansion cone, generate expansion forces, and it utilizes friction to resist the loads. Similarly, with displacement-controlled anchors like drop-in shell-type anchors, they utilize friction to transfer their tension stresses. Undercut anchors. Now, these anchors differ from the other mechanical anchors in that it uses bearing on the concrete surface to actually distribute their loads. If you look at this picture over here, you'll see that the actual bell shape over here is wider than the neck of the hole. So when the anchor is loaded up, it bears against the concrete, acts like a headed stud, and transfers the loads into the concrete. Typically, undercut anchors offer the highest load capacities of the different anchor systems and offer typically the best performance, but understand that usually undercut anchors tend to be a lot more expensive than the other systems that I show up here. Screw-type anchors also use keying to develop their capacities, and basically how they would work is you would drill out a hole and then use an impact driver to drive that anchor in, and the threads on that concrete screw actually cut into the concrete and hold in place. And finally, adhesive anchor systems. These work utilizing two different principles. One is direct bonding to the concrete, and the other is micro-keying. Certain adhesives require a roughened hole surface, so it requires that you drill the holes with a carbide tip bit to create a rough hole surface so that the adhesive can actually key into that concrete and hold in place. All right. So fundamental principles of anchor theory per strength design. All right, I know this slide is a little bit busy, but basically what we're covering here is the different failure modes that are evaluated for tension and shear. And these are evaluated via testing to establish performance of these anchor systems. So tension failure modes in anchor systems. And the thing is, I mean, this is not a bad thing. Understanding the different failure modes is important so that when you're designing, you can determine what the governing failure mode is going to be. Gives you a lot more predictability in your anchor design. So if you look at some of the basic tension failure modes, one of them is the steel element failure. What's happening here is the steel element actually ruptures and separates and breaks off. It could be a ductile failure or a non-ductile failure, but essentially what happens is that steel element breaks off. There's also concrete breakout failure. That involves the anchor actually pulling out a cone from that concrete. So a section of the concrete actually separates from the main slab and pulls out. That's called concrete breakout. Then you've got concrete splitting. This is typically applicable to displacement-controlled anchors and torque-controlled expansion anchor type systems, particularly when they're installed in thinner slabs, where splitting might occur. And once again, displacement-controlled anchors, what I'm talking about is like the shell anchors that are typically utilized in your industry for attaching scaffolding. And the torque-controlled anchors are like the wedge anchor systems that I'm addressing here. Side-face blowout is only applicable to cast-in-place anchors. And basically what happens here is when these anchors, like headed studs, are installed fairly close to the edge and tension to its capacity, what could happen is you generate these lateral bursting forces that could cause that edge of that concrete to blow out. Okay? So that's side-face blowout. Pull-out. That's applicable to mechanical anchors, and that's when the anchor actually pulls out without significant spalling of that concrete. There's also pull-through where for example, let's see, back. In this scenario over here, basically what you could have is if that anchor is over-torqued, it could pull through the wedges over here and pull out of that hole. Then you've got bond failure, which is applicable to adhesive anchor systems, and this is where the bond between the adhesive and the concrete, or between the adhesive and the steel element, actually fails and the anchor pulls out. Similar to the tension failure modes, you do get shear failure modes as well when the nominal capacity of that anchor is reached. So steel failure without a lever arm is basically when, like with the tension condition, the steel actually ruptures, causing the anchor to fail. Steel failure with the lever arm is applicable to those cases where there's a standoff condition. So here, what happens is there's a flexural failure that occurs. You can have standoff without clamping, standoff with clamping, or a grouted connection, but all of these could result in a flexural failure of the anchor system. Concrete breakout. Once again, you're talking about a section of concrete close to the edge breaking out when the capacity of it is reached. This is applicable typically when there are close edge distances. And concrete pry-out happens, and concrete pry-out is actually typically most applicable to cast-in-place anchors, but this happens when the anchor itself is stiff enough to preclude the steel failure from occurring, and when it's far enough away from the edge to make sure that concrete breakout is not what's causing failure. Okay? But basically with pry-out, what happens is a section of concrete on the back face of the anchor actually breaks off, pulls out. Okay, so strength design failure modes. These failure modes that we looked at, basically what testing establishes is the performance of these anchors for steel failure, concrete breakout, and things like that, and gives you nominal resistances that can be utilized based on the governing failure mode when you're doing your anchor design. Anchor design influence factors. There are various factors that affect the performance of adhesive and mechanical anchor systems, and these are some of them. They include the base material condition, type of concrete that you're utilizing, whether it's cracked or uncracked, the thickness of the concrete that you've got, the compressive strength of the concrete, important factor there, edge distance, how close is the anchor to the edge, how far are the anchors spaced from each other, how deep is the anchor embedded, and then which way is the anchor installed? Orientation, installation orientation. Is it installed overhead? Is it installed horizontally? Is it subjected to sustained load systems? And do we have to take into account seismic? Is it being designed or installed in a seismic zone? Base material condition. Here we're talking about cracked and uncracked concrete. And concrete as a product, as a material, actually works great in compression, but is very weak in tension. Hence the reason why we include reinforcement in concrete. Okay? The compressive strength of concrete is about 10 times that of its tensile strength. So what happens to concrete when it's in tension is it starts developing cracks. Even with reinforcement in there, it develops cracks. Microscopic cracks about 0.012 inches or so But those cracks do affect the performance of anchor systems. And you can see in this slide, back again, right here, that the difference between uncracked concrete and cracked concrete, when you've got embedment depth versus the design load plotted over here, you can see with cracked concrete, you get reduced capacities of this until you get bond failure or steel pull-out failure. So it is important to note whether you're designing with cracked concrete or uncracked concrete. And the requirement is, for a design engineer, is that they have to assume that it is cracked concrete unless they can prove that through the life of the anchor, that concrete is not going to crack. Okay? If you're designing in a seismic zone, you have to always assume that it's cracked concrete. Green concrete installations. So the code offers different criteria for how you address green concrete depending on whether you're designing or utilizing adhesive anchors or mechanical anchors. When it comes to mechanical anchors, the basic guideline is you shall not place the anchors in that concrete until it's achieved at least 7 days of cure. That's unless, of course, you've got additives added to kind of speed up the cure time of the concrete. And then the anchor capacity will be based on the concrete compressive strength at the time that that anchor system is loaded up. Whereas when it comes to adhesive anchors, the requirement now is that there should be a minimum 21-day cure, and if you install adhesive anchor systems with less than 21 days of cure, the capacities will be based on the compressive strength of the concrete at the time of installation, and also you would take a wet concrete or water-saturated concrete condition, which implies that there's a reduction in capacities that you're utilizing for the bond strengths of that concrete. Okay? So typically the recommendation is if you are going to be doing installations in green concrete, that you do field evaluations to ensure that the anchor system is suitable through maybe on-site testing. Minimum concrete thickness. So ACI 355.2, this test standard that I was talking about, provides guidance on minimum concrete thicknesses, but most of the values that are published for each individual different anchor systems is based on testing that has been done by individual anchor manufacturers. They will tell you what the minimum concrete thickness needs to be for their particular product. And understand that if you have an anchor system that is far away from the edge, where the edge distance doesn't interfere with the performance of the anchor, and the anchors are spaced far apart from each other, you might be able to install these anchors in thinner slabs. The minimum concrete thickness might be less for that. Concrete compressive strength, another factor that affects the capacity of anchor systems. So the relationship between compressive strength and the design load is actually linear. Basically what you can see here is it increases until you have steel failure occurring. The concrete compressive strengths that are utilized range from 2,500 psi to 8,000 psi. The models that are used for calculating the anchor systems, that is the optimal range for this. If you go outside of those ranges, then we recommend testing be done on site to evaluate how these systems will perform. And then there are also modification factors that need to be taken into account if you're dealing with lightweight or sand lightweight concrete. Okay? These are all included in ACI 318.14. Edge distance. Edge distance basically is the distance from the center point of the anchor to the edge. And there are two main distances that we look at with edge distance. There's the critical edge distance and the minimum edge distance. The critical edge distance is the point at which the adjacent edge no longer interferes with the capacity of the anchor. The minimum edge distance is the distance at which there's test data or values established for the capacity of that anchor. You can imagine as the anchor gets closer to the edge, the amount of concrete it has to work with gets reduced, and so the capacity decreases. And hence, we have the minimum and critical edge distances. But ACI 318.14 actually does publish guidelines, minimum edge distance guidelines. If there is no test data available for a particular product, there is code data that you can utilize to actually address that. For example, torque-controlled anchors will be 8 anchor diameters. Adhesive anchor systems would be 6 anchor diameters. Cast-in anchors, 6 anchor diameters as well. Anchor spacing. Similar to proximate edges, adjacent loaded anchors could also limit the amount of concrete that an anchor has to work with. And you can see it in this slide in terms of like overlapping cones. You see this concrete cone of pullout? The concrete right over there is being shared, so the capacity of these anchor systems is reduced. And once again, this is the anchor spacing is the center-to-center spacing of these anchors. The data that's available is typically based on testing, but once again, ACI publishes minimum spacings if there's no test data available for these systems. And note, if you're designing with mechanical anchor systems, sometimes they do offer different cases as well, depending on the spacing and edge distance. So for the anchor spacing, if it's fairly close to the edge, right, the minimum anchor spacing might be a little bit more than if it's further away from the edge, where there's not that edge distance reduction factor to take into account. Effective embedment depth. So the embedment depth is one of the most important determinants in the capacity of an anchor system because it governs the volume of concrete that's mobilized and distributed in the anchor stresses. Right? So here, the relationship is typically exponential. I had the chart up in my previous slide where it shows that exponential relationship between the load and the embedment depth. So it's typically to the power of about 1.5 until you get steel failure occurring. And something important to take into account with this one as well is that there is a nominal embedment depth and an effective embedment depth when it comes to mechanical anchor systems. The nominal embedment depth is the embedment depth when you first place an anchor, say for example, torque-controlled anchor. The effective embedment depth is once you've torqued up that anchor, so like for example with this mechanical anchor over here, right? The original embedment depth is over here. Once you start torquing it up, the anchor shank gets pulled up through these wedges over here, and this becomes the effective embedment depth. If you're trying to determine what the length of a particular anchor should be that you're utilizing, the way to do that is to take the nominal embedment depth, add the thickness of the fixture that you're fastening down, add the diameter of that anchor as well. So for example, for a 1/2-inch anchor, add a 1/2 inch on there to account for the nut and washer, and that'll give you the length of the anchor. Okay? And again, with the anchor theory, the embedment depths are also limited to a range that go from 4 anchor diameters to 20 anchor diameters. The maximum embedment depth for post-installed anchors is 20 anchor diameters. All right. Creep. So what we talk about with creep is when an anchor system is subjected to sustained loading conditions, it could displace, particularly when it comes to adhesive anchor systems. Okay? So there is testing criteria that establishes creep performance of different anchor systems. It varies on, it depends on various things like base material, the in-service temperature and things like that. But the test criteria or the testing that's done on this systems is basically what they would do is install the anchors, load those anchors up, elevate the temperature to 110 degrees Fahrenheit, and measure the displacement of that anchor over a 42-day period. Okay? Then they would extrapolate that data out, that curve out, to 10 years. And if the displacement exceeds a limitation that's set by ICC, that anchor is considered to be not creep compliant. Okay? The ICC reports actually will tell you whether an anchor is suitable for creep applications, for sustained loading type applications. Installation orientation. There is a difference between installing an anchor straight down versus installing it overhead or upwardly inclined. Right? There are various different methodologies that actually are utilized to actually install anchors, particularly adhesive anchors overhead versus straight down. And now the codes actually require installers be qualified and certified when they're installing anchors horizontally to upwardly inclined. the anchors that are subjected to sustained loading conditions, what I was talking about in my previous slide over there. So improper installations, what could happen if the anchor system, like an adhesive anchor system, is improperly installed? Why you see losses in capacity? So take, for example, over here, where you have sag of the anchor element due to the anchor curing time. So basically what happens is you've installed this adhesive system, and the steel element actually sags out. You're reducing the embedment depth, hence you're going to get reduced capacity from that anchor. Incomplete coverage of the anchor element due to run out of the adhesive. So you've got a really runny epoxy type system that you've injected into the hole. You stick your threaded rod or anchor element in there. The adhesive starts dripping out. You're going to get reduced amounts of adhesive in there, which means reduced capacity. So reduced coverage of that steel element, so reduced bond strength. Similarly, entrapment of air. So if the adhesive is injected, say, overhead, and there are voids left in that hole as the anchor is being injected and installed, basically what that means is that the steel element does not have enough coverage and the bonding surface is reduced, hence reduced capacities. So actually, with this, I should point out that for adhesive systems, they are qualified by ICC for overhead and horizontal installations. The ICC utilizes the processes that the manufacturers say this is how these anchors need to be installed overhead to qualify, see if they work, and qualify them for overhead installations. Seismic design considerations. If you are doing work in areas that are seismic design categories C through F, there are certain considerations that need to be taken into account for your anchor design, and these are based on whether the connection is going to be a ductile failure of the anchor element, a ductile failure of the actual attachment system. So that needs to be taken into account, and that's also addressed in ACI 318, 14, and Chapter 17. So, design verification. We talked about the different failure modes, the tension failure modes and the shear failure modes. What they give you, along with the base material thicknesses and such, is the design strengths that you can utilize. So it gives you nominal resistances, which you can multiply by a strength reduction factor, a phi factor, to get your design strength, which you would compare with the factored loads that you have for your particular attachment to determine whether that anchor system would be suitable. And if you've got combined loading as well, something else that needs to be checked is this interaction equation right here. It's a trilinear equation that basically offers a check to make sure that the anchor system works with combined loading, so if it's subjected to both tension and shear at the same time. Anchor selection. So there's a whole slew of different types of anchor products out in the market right now. We can break them down into cast-in-place anchors, mechanical anchors, and adhesive anchors. And basically what you've got is anchors like headed studs and J-bolts. These are cast-in-place anchors. Anchor channel systems, which maybe will give you a little bit more adjustability once the anchor has been installed. Threaded inserts that can be installed. These are primarily for concrete. You also have mechanical anchors that are suitable for concrete and masonry applications. These include things like the undercut anchors that I was talking about, wedge-type anchors, which uses an expansion principle to actually set the anchor and distribute the loads, and screw-type anchors, concrete screw-type systems. Wedge anchors, they've been around, for, I guess since the 50s or 60s or so, right? And they're very popular in the industry right now. However, we're seeing screw anchors taking a bigger chunk of the market from wedge anchors. They seem to be popular with contractors because there are certain things that they offer that the standard wedge anchors don't. Once you've installed the wedge anchor, that's set. If you need to get rid of them or pull them out, basically you've got to cut them off or burn them. It's very difficult to remove once those anchors have been set. With the screw anchor, since the installation process is to drill out the hole and use an impact driver to drive in the anchor to set it, if you need to remove the anchor, basically what you can do is flip that impact driver into reverse, pull the anchor, back the anchor right out. So if you've got an installation that's not a permanent installation, you can set the anchors, and once you're done with it, reverse it and pull it back out. There are now some screw anchors out in the market that are reusable as well. They've got technology built in to be able to reuse that anchor, removable and reusable. Then when it comes to adhesive systems, two main types of adhesive systems are the slow cure and fast cure adhesives. Okay? When you're looking at utilizing an adhesive anchor system, there are certain things that need to be taken into consideration. One is the cure time of the product. Some products cure up in like 30 minutes, others take a day, others take maybe even 4 days at room temperature to achieve full cure. So cure time is an important thing to look at with adhesive systems. And then also the temperature range at which it can be utilized. So some products can be used at much lower temperatures than other systems. Certain products, I have seen adhesives out in the market that the minimum temperature at which it can be utilized is 71 degrees Fahrenheit, which for us in Chicago is almost never. And yeah, so that's something else that needs to be taken into account. Something else that's very, very critical when you're looking at adhesive anchor systems is hole cleaning. The presence of dust, debris, and such in the holes can tremendously affect the performance of adhesive anchor systems. So it is important, it's critical actually, to follow the manufacturer's printed installation instructions in cleaning out the holes with the prescribed number of wire brushing strokes. In fact, I have a slide that'll show you that, and using compressed air to blow out the dust to make sure that that hole is cleaned properly. So, showed you a whole bunch of anchors over here. Now, how would you go about selecting a product that would meet your needs? Right? Most manufacturers offer anchor selected charts. These charts actually give you, for different conditions, exactly whether these anchors are qualified or not. So it'll tell you, can this anchor be used overhead? Is it suitable for concrete, wet concrete? Can you use it in brick or grout-fill block? So these anchor selected charts are a good reference to be able to go in there and find out whether your anchor would work in a particular condition. Then the hole cleaning that I was talking about for adhesive anchors, once again, there's no industry standard as far as, that manufacturers have to follow as far as hole cleaning is concerned. Some manufacturers might say, okay, our hole cleaning process is drill out the hole, blow it out twice with compressed air, brush it out twice with a wire brush, blow it out again twice with compressed air before you inject adhesive to establish a clean hole, right? Others might say you have to blow it out 4 times, brush it out 4 times, blow it out 4 times. Yet others might say you've got to do that and then repeat all those processes 4 more times. So there's no industry standard as far as hole cleaning goes. But the typical process involves using compressed air and a wire brush to get it properly cleaned. There's also an additional method that you can actually ensure proper cleaned holes. These are becoming very popular in the market now. It's hollow drill bit systems. These are attached to vacuums where as the holes are being drilled out, the dust gets sucked out, right? And so there's no going back and having to blow out the holes and brush them out and suck out the dust. Blow out the dust again. And these vacuum systems actually serve an additional purpose in that you guys might be familiar with the new OSHA silica dust standard that's out in the market right now. It was implemented last year, and basically what that entails is OSHA regulates that there's only a certain amount of particulates that can be released out to the air during the construction processes. They measure, they check, and you could get heavily fined if you fail to meet that criteria. And part of that criteria requires that if you are doing hole cleaning like this, you can imagine if you're blowing out a hole, you're going to get plumes of dust going out in the atmosphere, right? So that introduces a lot of particles into the atmosphere. So in those situations, when you're doing this, you have to have a HEPA filter to be able to collect the dust. With using a vacuum system and the hollow drill bit type systems, the dust is collected, that's considered OSHA Table 1 compliant. So when you're utilizing a system like that, you no longer need to have your contractors wearing respirators or use HEPA filters to collect the dust. This system with the hollow drill bits is applicable to adhesive anchors. I think it was originally developed to address adhesive anchor systems because hole cleaning was a lot more critical for adhesive anchors than mechanical anchors. But now mechanical anchors too are getting qualified for use with hollow drill bit type systems. Anchor design resources. So how do you go about designing anchors? There's three main methods that you can utilize. One is software. A lot of manufacturers provide anchor design software that you can utilize. Most of it is free of charge from their websites. Simplified design tables. These are there once again to help you avoid having to do 7 pages worth of calculations. However, if you're one of those people that enjoys doing calculations or would like to do 7 pages worth of calculations, you've got the ACI 31814 codes with all the equations that you can utilize, you can follow to do your anchor design. What the anchor software typically offers is as you change parameters within it, it'll do the calculations for you. It'll automatically change the calculations for you. With the ACI 31814 calculations, you could do 7 pages worth of calculations, reach the end, and find out that that particular anchor that you were trying to design with doesn't work. So you got to go back to the beginning, start again with a different anchor, do another 7 pages worth of calculations. The software typically simplifies that process. And then the strength design tables, the simplified design tables. I talked about allowable stress design versus strength design. Allowable stress, maybe not the most predictable design methodology or evaluation methodology for anchors because of that, not taking into account the statistical scatter of the anchor results and things like that. But one of the things that was easy with allowable stress design was, as a person trying to figure out the capacity of an anchor system, what you could do was look at a table and say, I want to use a 1/2-inch anchor, embed it 5.5 inches deep in 4,000 psi concrete. What's the capacity I can achieve from this anchor system? So it made it really simple to actually find out what capacity that anchor could hold. When we went away from allowable stress design to strength design, there was a lot of complaints from designers saying, hey, look, you've taken a process that was really, really simple and made it a lot more complex. We understand that the predictability is great. I can figure out exactly what the failure mode is going to be, but this is a lot more intense, a lot more difficult. And so manufacturers have now provided strength design tables, which are structured the same way those allowable stress tables were structured, where you can go and say 1/2-inch anchor, 5.5-inch embedment, 4,000 psi concrete. This is the design strength that I can achieve from this. Okay? So, summary. Anchors can be designed for various loading conditions, including static, dynamic, and seismic loads. Strength design provisions evaluate all the possible failure modes for both tension and shear for different anchor systems. Then the different types of anchors include cast-in-place anchors, adhesive anchors, and mechanical anchors. Various factors can influence the anchor performance. These include embedment depth, edge distance, spacing, and the condition of the base material. So whether it's green concrete, cracked concrete, thickness of the base material, etc. Post-install anchors must be pre-qualified via testing to obtain recognition under the International Building Code. So that pre-qualification criteria that exists enables manufacturers to get qualification or recognition under the International Building Code. And there are various resources that are available out in the industry to help you select and design with the different anchor systems that are out there. Good. Questions? There's a lot of information that I threw at you there, so yeah. I tried not to make this too technical, so if anybody wants to get a little bit more technical on this, I'd be happy to do so too. If you want to talk about lambda factors and psi factors, we can do that as well. No questions? All right, so I am going to be, oh, wait, we do have a question here.
You use your epoxy. What's the life expectancy of epoxy in the concrete if the wall's passed by an engineer? Sorry. When you use epoxy and you get the walls passed by an engineer and you have your depth embedment and your anchor rod you put in, what's the life expectancy of the adhesive? We know you got to test them on a yearly basis. I mean, every 5 years, but what's life expectancy on the adhesives?
That's an excellent question. And did everybody answer that or hear that question? That was basically, what's the life expectancy of the adhesive system once it's been installed in a building? It is the life of that building. So if it's 50 years, 100 years, it's the life of that building. So to evaluate that, I mean, the company that I work for has been in this business for decades, more than half a century. And there are fields of spring pots, loaded anchors, where we are still evaluating from like the very first adhesives that we developed and introduced to the market. We're looking at displacement, the performance of those anchor systems. So fields of loaded anchors that we're actually utilizing to evaluate the performance of these systems.
Just one more question. Where we come from, there's a discrepancy in the field between some engineers. When you do epoxy anchors, we pull test as a body of minimum 3, if not 4, with a plate. Do you ever torque test one individual rod on an epoxy to a number?
Yeah. So I know that there's the standard for testing adhesive anchor systems is actually pull testing them. The concern with torque testing of adhesive anchors is if that anchor rod is over torqued, basically what can happen is you can have the bond breaking, which reduces the capacity of the anchor. And that over torquing also is, so say for example, you've got a burr in that thread where the nut jams up. That could cause problems and cause the anchor to actually break the bond and pull out. So recommendation is not that you torque test adhesive anchors. You know, when it comes to mechanical anchors, wedge type anchors, yes, that's typically done. Torque testing of adhesive anchors doesn't really give you much as far as results go. Good question. Any other questions? Yes.
Okay, we were using the software to do some anchor sizing, and it's typical for people in our industry to go into the edge of a slab. So you've got a concrete slab on a brand new building, and we were looking at an 8-inch slab. So we started running some numbers with larger anchors, and because if you put one in the middle of the slab, you have a 4-inch edge distance, okay? So the larger anchors, it would not give us satisfactory results, and we ended up using something that was rather surprising, like a 5/8-inch anchor, which is not something that we were expecting. And I was just wondering if you're not putting shear forces in the up and down direction, the only shear forces that you will experience would be horizontal. Does that change the effects?
So basically what you get with that condition is, imagine that concrete cone of breakout that I was talking about. And so you've got a slab that's yay thick. You've installed an anchor there, right? A larger diameter anchor would have a bigger concrete cone of breakout. And so with the smaller anchors, maybe you can minimize that angle and utilize more of that concrete as opposed to pulling out a large chunk. That's kind of why that software would have spat out.
It just seemed like it was rather surprising results. I mean,
Right.
And we normally wouldn't put some of the heavier equipment up using that small of an anchor.
Okay. Also, just keep in mind when you're doing your design as well, most of the anchors are tested in unreinforced concrete. So, it does limit, I mean, basically the results that you're getting are fairly conservative with these systems. But if the software tells you that it can do it, double check with, most of the software actually provides you with reports that show the exact calculations that were utilized. I would do a double check with that just to make sure that it works. And yeah.
Yes, sure. Okay, thanks.
Thank you. Good question. Yes.
So I got a question when it comes to like the if it's being used for life safety, the expansion anchors in comparison to the adhesive anchors, are there restrictions on using the expansion versus the adhesive?
No, there are not restrictions on them. I mean, so there's There are different categories of anchors as well, depending on the reliability of the anchor system. However, basic wedge anchor type systems have been qualified for use in life safety applications, as have standard adhesive systems. So there is no difference on that. If a product maybe does not have an ICC report that I was talking about, I might be a little bit cautious in utilizing that for life safety applications.
Okay, thank you.
Other questions? Yes.
Allowances for post-tensioned concrete as versus regular reinforced concrete.
Okay. So I guess the issue with post-tension concrete is, you don't want to hit the strands and all that when you drill in the holes, right? That's the big thing. If you can locate the strands and install the anchors in between them, then you've got a lot of suitable anchors for it. I've had engineers actually design when they're only able to embed anchors maybe an inch into those PT slabs because they want to avoid hitting the strands. There are particular ones like the shell anchors that are utilized for that. Currently, there are not too many shell anchors or drop-in anchors that have ICC evaluation services reports, but unfortunately, the industry is limited when it comes to that for shallow embedments where you're trying to avoid PT strands.
On a slab edge, if you're say 2 feet from the post-tensioned cabling, as opposed to a little further or even closer,
Yeah.
is there any difference in your thoughts on what you have there? Because keeping in mind that the post-tensioning concrete is usually not at the very face. So
Yeah.
when we do something, we try to shove it back in as far as possible on a slab edge, so we do have some strength there.
So in those scenarios where it's not close to the PT cables and all that, it's absolutely suitable for use.
All right.
Thank you. Great questions. Yes.
A common issue that we come up against is when scaffold's being installed for facade work around a structure that's either made out of brick or some sort of high-end marble, where the only real anchoring location is going to be at the joints into either a grout or some sort of seam. So you don't have a whole lot of material to tie into.
Yeah.
Is that something you guys have looked into? And is there kind of an anchoring system you could recommend?
Yeah. So there are certain adhesive systems that we have actually tested in the bed joints and head joints of those conditions. I know in your industry, one of the popular products that's utilized is shell anchors, drop-in anchors for that condition. And I think the requirement is that they be installed in the bed joints or head joints when they're utilized. I don't know of any manufacturer that actually publishes data for drop-in anchors in that condition, but I know it's heavily utilized. However, there are adhesive systems that have qualification for installation in those. Yeah. Great question. No other questions? All right.